Earlier, we studied the non-inverting amplifier and the inverting amplifier. If two voltages are both applied to the inverting input, a summing operation can be achieved. As shown in the diagram, two signals are fed into the inverting input. Using the virtual short and virtual open properties of an ideal op-amp, we have Vn equals Vp equals 0 and I equals 0. Applying Kirchhoff's current law, KCL, at the inverting input, II plus I2 equals I3. That is, Vi1 minus Vn divided by R1 plus Vi2 minus Vn divided by R2 equals Vn minus Vo divided by R3. Substituting Vn equals 0 gives negative Vo equals R3 times Vi1 divided by R1 plus R3 times Vi2 divided by R2. This means the output voltage equals the sum of each input voltage scaled by different ratios. The negative sign indicates the inversion caused by the inverting input. If R1 equals R2 equals R3, then it becomes negative Vo equals Vi1 plus Vi2. If an additional inverting stage is connected to the output, the negative sign can be eliminated, achieving true arithmetic addition. Therefore, this circuit is also called an addition circuit. Non-inverting summing amplifier. A summing amplifier can also be built using a non-inverting amplifier. As shown in the diagram, two more signals are connected in parallel at the input of the non-inverting amplifier, feeding into the non-inverting input. Using the virtual open property of an ideal op-amp, we have Ip equals In equals 0. The current equation at point P is I1 plus I2 plus I3 equals I4. This means the difference between Vi1 and Vp divided by R1, plus the difference between Vi2 and Vp divided by R2, plus the difference between Vi3 and Vp divided by R3, equals Vp divided by R4. With the virtual short condition where Vp equals Vn, after substitution and rearrangement, we get Vo is equal to the quantity 1 plus the ratio of Rf to R, multiplied by the sum of the reciprocals of R1, R2, R3, and R4, and then multiplied by the sum of Vi1 divided by R1, Vi2 divided by R2, and Vi3 divided by R3. The output voltage is equal to the sum of the individual input voltages. For this non-inverting summing amplifier, assuming that the parallel combination of R1, R2, R3, and R4 is equal to the parallel combination of R and Rf, the superposition principle can be used to solve it. Let Vi2 and Vi3 be 0, and find the output voltage when only Vi1 is acting. Vo1 equals 1 plus the ratio of Rf to R, multiplied by the ratio of the parallel combination of R2, R3, and R4 to the sum of R1 and the parallel combination of R2, R3, and R4, all multiplied by Vi1. Similarly, we can obtain Vo2 and Vo3 when Vi2 and Vi3 act alone. Their forms are the same as that of Vo1. Vo equals Vo1 plus Vo2 plus Vo3, which is equal to 1 plus the ratio of Rf to R, all multiplied by the sum of the parallel combination of R2, R3, and R4 divided by the sum of R1 and the parallel combination of R2, R3, and R4, times Vi1, plus the parallel combination of R1, R3, and R4 divided by the sum of R2 and the parallel combination of R1, R3, and R4, times Vi2, plus the parallel combination of R1, R2, and R4 divided by the sum of R3 and the parallel combination of R1, R2, and R4, times Vi3. This configuration achieves the summing operation. Because the voltage at the non-inverting input of an integrated op-amp depends on the series resistances of the individual signal sources, the signal sources are not independent of one another. As a result, when one branch resistor is adjusted to achieve a desired proportional relationship, the ratio between the input and output voltages of the other branches will also change. This makes estimating circuit parameters and tuning the circuit more troublesome. In addition, since there is no virtual ground, the integrated op-amp will be subjected to a certain amount of common mode input voltage. That concludes today's lesson. See you next time.